Hi everyone. So today, previously we had discussed on the Ben-Munford algorithm, right? So today we'll be discussing on the topic Floyd Warshall algorithm, right? So let's get into the definition part. The Floyd Warshall algorithm is a dynamic programming algorithm, right? So it uses dynamic programming. So Floyd Warshall algorithm is a dynamic programming algorithm used to find the shortest paths between the all the pairs of the vertices in a weighted graph, right? So it works with both directed as well as the undirected graphs and can handle negative edge weights, but not the negative cycles. See, Bellman-Ford algorithm can handle the negative weight edges, negative edge weights, as well as the negative cycles as well, right? So previously we saw the same. So here, the only difference between the Floyd-Warshall and the Bellman-Ford algorithm is that this it works with both directed and undirected graphia and can handle the negative edge weights as well, but it cannot handle the negative cycles, right? So this is the main difference between the Bellman-Ford as well as the Floyd-Warshall. So let's get into the explanation part. Just listen to this carefully. The same thing will be implementing in the form of algorithm or the code, right? So the main idea here is that the algorithm tries to improve the shortest distance between any two vertices I comma j, right? So what it does, it tries to improve the shortest distance between any two vertices I comma j just by checking whether there exists an intermediate vertex k that makes the path from I to k and k to j shorter than the currently known path from I to j, right? So formally, for each vertex k as an intermediate node, we update the distance matrix, right? For each vertex k, right? For each vertex k, we update the distance matrix. And so we'll be going with this formula, right? Distance of ij equals minimum of distance of ij, comma, and ik as well as the kj, right? Ij, ik as well as kj, right? So this runs for every combination of ijk. So same thing here, right? So intermediate vertex k that makes the path from I to k to j shorter that than the currently known path from I to j, right? So this runs for every combination of I comma j comma k, resulting in the time complexity of this one big O of v cube. Nothing but this v is nothing but the vertices or the vertex, right? So big O of v cube. So this is it for the explanation part. Now, rather than explaining more theoretically, let's do one thing. Let's start writing the code. Let's try to implement the same thing in the form of algorithm using Python programming language or the code, right? So first, let's start with the this one. What do we call? Let's move on with the first step here. Let's define the large number just to represent the infinity for the unreachable nodes. There might be unreachable nodes present, right? So for that, we'll be assigning that one to the infinity basically, right? So I'll just go with here inf equals float. Let me give here inf, right? This is fine. Now let's move on with the second step here. Let's define the graph as an adjacency matrix, right? So you can just draw the graph here. If you draw the graph, you'll understand that this even better basically. Right, so let me go with 0, 5 here. This is 5. Let me go with infinity, value infinity, meaning not reachable, right? So not reachable in the sense unreachable nodes basically, right? So this is fine. Next, let's go with inf uh, 0, 3, infinity, right? So this is also fine, man. Next step, let's go with infinity. We go with infinity twice here, right? Then 0 and 1. Finally, let's go with infinity. Hmm, infinity, let me go with the infinity thrice here. Yeah, and finally, let me give 0 here. So this is the adjacency matrix basically, right? So what we are doing here, we're just defining the graph as an adjacency matrix. So we are not going with a adjacency list here. We are going with the adjacency matrix, right? So this is fine, man. Now what we will be doing, let's move on with the step 3 here. Number of vertices in the graph, right? So let's initialize this one to, or let me assign this one to the length of the graph, right? So this is going to be the graph basically, right? We have considered the adjacency matrix here. Now, let's move on with the fourth step. Nothing but let's create the distance matrix, right? When I say distance matrix, initially, it's initially the copy of the graph itself, right? So I'll just go with this here. This one, let me give it in this form. Row within the right. So this is fine. Yep. For row and graph, right? For row and graph, this is also fine. Now let's move on with the fifth step here. So let's apply the Floyd Warshall algorithm, right? Let's apply the Floyd Warshall algorithm. Now, first step here is, as I have said, as we had discussed. So the time complexity would be weaker, right? So we will be going with the three nested loops here. One for each possible intermediate vertex, second one for each source vertex, and the third one is for each destination vertex. Simple. So let me give you for k in range. So let me go with v. This is fine. Next one for I in range, again v. uh what happened here? Why this is showing like this? Expected. So here for k in range of v, have written correct itself, right? Oh yeah, this is correct, right? For I in range. What happened to this one? Expected expression after n. Oh yeah, twice I have given in here. Yep. This is fine. Now, um, also we have to consider for each destination vertex as well. So I'll just go with for j in range. Again, let's pass v here, right? Three things we have considered here for each possible intermediate vertex. First one k actually, for each source vertex I, for each destination vertex j. Here source vertex I, destination vertex j, and for each possible intermediate vertex k, right? So this is fine. If the path through the vertex k, right, k is shorter, then we have to update the distance, nothing but dist of ij, whatever we have considered, that one we have to update, right? So let's write that. If so, I can just write it in this way. If dist of ij, let me go with dist of ik here. So this one plus dist of kj less than dist of this one ij, right? So this is fine, man. So what we'll be doing here? So this one dist of ij is equivalent to dist here I k less uh, distance of kj, right? So I'll just go with a k. Right, so this is fine. Now let's do one thing. Let's move on with the further steps, right? So let's print the final shorted distance matrix, right? So I'll just go with a print here. Let's go with a print just for the interactive purpose. I'll just go with shortest distances between every pair of vertices, every pair of vertices, right? So this is fine. So for I in range, for I in range, let me go with V here. For j in range, let me go with again V here. This is fine. If distance of I j, if it is equivalent to infinity, then what we will do? Let's print here. Yeah. Let's print infinity with end equals. So let's leave space here, right? So this is fine. And let me write one else here. This is just for the this one man example usage, right? So I'll just go with else here. Hmm. print in this way. I'll just go with, let's print the distance here. Distance, let me pass I and j. Yep. So we'll just go with end equals. Let me leave the space here. Finally, let's call the print here. So this one for, yeah, I'll just go with a print, right? So this is fine. Yeah. Now we are done with the code, right? So let me explain this one before running the code, right? So here infinity equals float of something, whatever I have written here, the first line, it sets the this one large value representing the infinity. Basically it is used for the unreachable paths. I have said this one multiple times. Graph equals this one, right? So this one basically we are defining the adjacency matrix for the graph, right? So inf here, this one I have said, this one inf means no direct edges here, right? It says that there is no direct edge, right? So this is fine. V equals length of this one graph, whatever I have written. So this gets the total number of vertices, nothing but 4 here in this case. It is 4, right? Here in this case, whatever the graph we have considered. In that graph I'm speaking of, right? So I'm relating that one to the graph basically. Now distance equals whatever I have written, line number 31. So this one, this copies the graph matrix to the distance just to preserve the original graph, right? So this is fine. For k equals range, whatever I have written, so we are iterating through all the vertices in the intermediate as intermediate nodes. This one, the second for loop, this iterates through all the source vertices, and this third one, the third for loop, basically it iterates through all the destination vertices, right? So if destination this one, if distance of this one ik, so this one whatever I have written, this checks if the going, this checks if going through vertex k gives the shortest path from I to j. If it does, then we will be updating basically, right? This one, line number 37. Basically, we will be updating the shortest path distance if found shorter. Right. Finally, let me tell you one thing. The nested loops, whatever we have written here, the algorithm ends here, right? At the line number 37. The nested loops, whatever we have written, 3 nested loops, uh, it ensures that all the pairs I comma j are optimized using every k, right? So this is it for the algo, simple one. So from the line number 39 to 46, this is just the this one example usage, right? So we'll be getting the shortest distance between every pair of vertices, right? So in our case, so shortest distance between every pair of vertices has to be 0,589, right? So first one here 0,589, so output has to be, wait, I'll show you whatever code that we have written for whatever graph we have considered this one, right? So our output has to be shortest distance between every pair of vertices has to be 0,589. This one infinity, I'll just write I here, 0. So I'll just write in so that we don't get confused. 0, 3, 4. Third one here, infinity twice. This is fine. 0, 1. So here the fourth line, infinity 4 times, right? Infinity, infinity, followed by the 3 infinities here. Total 4. So this is the output that we need to get here, right? So how? See, I'll just explain you. Just listen to this. So distance 0 to 2 becomes 8 here, right? Distance, so I can just draw the graph and you can just check here. Distance 0 to 2, right? Distance 0 to 2 becomes 8, right? So this becomes 8. Why it becomes 8? Because 0 to 1 to 2 is shorter, right? Is shorter. So we will be going with 5 plus 3. We'll be going with a 5 plus 3. So this becomes 8 here. This is fine. So 0, 5 remains same. Instead of the infinity, this becomes 8, right? So now we have the directed. We can consider the shorter one, this one, 8. This is fine. Now we have the same value, right? So we have the same value for this one. Infinity fine, 0 fine, 3 fine, 4 also fine. We have the so here we have the different value for this one, for the last one, and for the 10 we have 9 here. How it is 9 here? So again, distance of 0 to 3 here, right? So this is 0 comma 3 itself, right? 0 comma 0, 0 comma 1, 0 comma 2, 0 comma 3. Distance 0 to 3 basically becomes 9. Why it becomes 9? You can just check here, because it will be 0. It will be from 0 to 1 to 2 to 3, right? 0 to 1 to 2 to 3. So this is shortest, and we will be going with 5 plus 3 plus 1. We will be going with 5 plus 3 plus 1. So this will be basically 9. 8 plus 1, it will be 9, right? So this will be 8 and this will be 9, right? So this will be 5 plus 3 will be 8 and this will be 9, right? So this is fine, I believe. So this is fine, I believe. So this one we got here 8. So this one we got 9. Yep. So 8 and 9. This is how we got change. So now we have infinity 0, 3 and infinity. This remains same. So this infinity, sorry, in the place of infinity, we have 4, right? So distance, this is 0 comma 0, this is 1 comma 0, 1 comma 1, 1 comma 2, 1 comma 3, right? So from distance 1 to 3, from distance 1 to 3, this becomes actually 4. Why it becomes 4? The shortest distance here is this one. You can just look at the graph. So that if you have drawn, so this will be 1 plus, sorry, I'll just represent in this way itself. This will be shortest path will be 1 to 2 to 3, right? So this is shorter basically. We can just go with 3 plus 1. The value will be, the weights will be 3 plus 1 basically. It will be 4. So in this case, we will be going with a 4 instead of the infinity, right? So I hope this is clear. These are the three edges, right? I mean, these are the three values that we have updated. Then comes the this one third row, right? So infinity in twice infinity 0 and 1, right? So twice infinity 0 and 1. This remains same for the third row. For the fourth row, we have in this one infinity thrice and 0 once, right? So this 0 becomes infinity here. Why it becomes infinity? See, some remain infinity here. So from 1 to 0 or 2 to 0, because there is no path connecting those vertices at all, right? So this one as well, there is no path connecting this vertex, this vertex, yeah, this vertex actually. So this will be 3 comma 2, 3 comma 3, this one 3 comma 3. So for the 3 comma 3, we have this one. There is no path actually connecting this vertex, this particular vertex for 3 comma 3, right? In this case, instead of this one, what do we call 0? We will be representing this one in the form of infinity itself, right? So this is how these four edges are updated here. The resulting this one in the resulting in the result basically, or within the output, right? So let's try to run the code. Now we have the idea, right? So this is the output that we need to get: 0589 infinity 034. These three these things are updated basically. Infinity to 8, 10 to actually 9, and infinity to 4, and this one 0 to infinity, the last one, right? So let me delete this one. Let me do one thing. I'll just copy the entire file name here. Let me give Control J. Let me give Python file name dot py. Right, see here 0589. This is changed here. So this one again 03 remains same, infinity 03, 4 got changed here. So this remains same, infinity infinity 01, thrice infinity followed by 0, right? So yeah, here and we are left with 0 itself, man. I showed you that we'll get infinity, right? Sorry. This will be 0. This is represented by 0 itself, right? So yeah, sorry. This one I showed you wrong, I believe. The last value. This remains 0 itself, man. Sorry. Yeah. This is fine, I believe. Right. So this is it for the output. So I have explained you already how we got the output. So one change, actually, this remains 0 itself. Don't get confused, right? So this is fine. Now, as we have the knowledge on the this one Floyd Warshall algo, we are done with the algorithm. This is it for the algo, right? So let me summarize whatever we have learned so far, right? So just try to keep these 4 to 5 points in the head, right? So first thing here would be Floyd Warshall finds the shortest paths between all the vertex pairs using dynamic programming, right? Again, let me tell you, Floyd Warshall finds the shortest paths between all the vertex pairs using dynamic programming, right? So this is one thing. So it updates the distance matrix by checking all the intermediate vertex, right? So it updates the distance, this one matrix, by checking all the intermediate vertex. So this part, sorry, yeah, right? Intermediate vertices, right? So the time complexity here the time complexity of the algorithm is big O of v cube, as I've said, and the space complexity of the algorithm is big O of v square, right? So big O of v square. Just remember this one. This is very important. So the time complexity would be big O of v cube, three nested loops here. The space complexity would be big O of v square, and this handles the negative weights but not negative cycles. Negative cycles are handled by the Bellman-Ford algorithm. It handles positive values, positive weights, negative weights, as well as the negative cycles, right? Bellman-Ford algorithm. Dijkstra's only handles the positive weights, right? Floyd Warshall handles the positive weights and the negative weights, but not the negative cycles, right? Just remember this one. While we are asked certain questions in the this one contest based on this one graphs, so you this might be very handy, right? So you should be knowing what to this one implement, basically whether we have to implement Dijkstra's, whether we have to implement Bellman-Ford, whether we have to implement this one Floyd Warshall, or whether we need to implement this one Johnson's, right? So we need to know that at any cost we need to know, right? So this is fine, I believe, right? Simple one, right? So we are done with the Floyd Warshall algorithm, right? So next we'll be discussing on the this one Johnson's algorithm, right? For now, this is it. Thanks for watching, guys.